Okay, so we're up to the next lesson, which is numerical integration. And again, this is one that I would have done last week because that last one was a bit short. So it means I would have got 2 into the lecture at that time. Right, so we know to work out integration, well, we know to work out some integration already. Numerical integration, we use this if we can't work out, if we don't know how to integrate f of x, but we still want to know the area of a region. Okay, so what we do is we approximate the area under the curve. Okay, so what we have, imagine a curve like so. I'll try and do it similar to the one in the book, which looks like this. Okay, so that's supposed to be a straight line. What we do is we approximate it by splitting it into splitting the area under the curve into trapeziums, like so. Okay, so that's supposed to be a straight line there. These are all supposed to be straight lines. Now the area of a trapezium is a half. If we've got a trapezium which looks like this, that's A, that's B, that's H. Half the sum of the parallel sides, which are A and B here, these are going to be these here, times H, the distance between them. And that's the way the formula goes for the area of a trapezium. Okay, so this is y is f of x, but we don't know how to integrate f of x, but we can work out all these triangles. So that, all these, we can work out the area of all these trapeziums. x0, x1, x2, x3. So these are all distance h between them here. Okay, this one, this height here, this is y0. This one is going to be y1. This one is y2, and this one is y3. Okay, so there we go. So this first one here, trapezium number 1, that's going to be using this formula here. It's a half y0. This, see, that will be the A and that will be the B. And then for the next one, that's the A, that's the B. For the next one, that's the A and that's the B. Okay, so what we've got, the first one, the area of this one is a half, and it's y0 plus y1 for the heights. So we don't really need those A's and B's, because it's y0 and y1 times h. That one is a half of y1 plus y2 times h, and that area is a half of y2 plus y3 times h. Okay, so we're going to add all those up. Now, because for each of them there's a common factor of a half, or a few common factors, a half and h in each one. So here, look, taking the half and h outside the bracket, then you've got y0 plus y1, y1 plus y2, y2 plus y3. So these are all these here, put together in a single formula like that. So that's the area, is approximately equals to, there we are, add them all up. Okay, and what they do here, look, because y1 is used in the first trapezium and the second one, you have 2y1, then y2, all the way up to the second to last one, and the first and last one just gets used in one trapezium. So they're added, they're y0 plus yn plus 2, all the others added together. Okay, so let's have a look at this one. We do a diagram. I'll copy it from the book, because this is on the top of page 473. So this diagram is y equals root of log x. Okay, that's 1 there. These are the x's, these are the y's. So that's the diagram there. And it says for x greater than 1, that's because when it's less than 1 you can't take the square root of a negative number. Log of a number less than 1, between 0 and 1 is negative. Right, use the trapezium rule with 4 intervals to estimate the value of the integral between 2 and 4. So that's 1, 2, 3, 4. We want 4 intervals, so we're going to have this 1, 2. Okay, so the 4 intervals, we're going to split these into halves as well. So there's our 4 trapeziums. Give you the answer to 1 decimal place. Part B, explain why it gives an underestimate. It's because the curve is concave down. So the trapeziums are underneath the, each trapezium is underneath the curve. So the actual area is going to be slightly less than the correct area. Explain why increasing the number of intervals gives a better estimate. It reduces the error. It's it's just more accurate. More accurate because it gets, the more that you've got, the less of the, so if it was like this, let's just do, and that was the top of the curve. If you actually split it, so that was 1 trapezium, because if you split it into 2, it becomes, you collect more of that, more of the error area. Right, so let's have the x's. 2, 2.5, 3, 3.5 and 4. Okay, and then the y's for these, that's going to be the square root of log 2, square root of log 2.5, square root of log 3, square root of log 3.5, square root of log 4. Oh, they've got the answers in the book here actually. The same we do it on a calculator. 0.83, 0.96, 1.05, 1.12, 1.18. Okay, so the area, so the trapeziums, so it's a half, and it's going to be, we've got the first one, it's 0.8, it's a half. It's a half h, a plus b for each trapezium, and h is a half, so it's a half times a half. That's the h there. That's 0.5 because they're going up in steps of 0.5. And there's a half from the formula already. So it's 0.83 plus 0.96 for the first one, plus 0.96 plus 1.05 for the second one. The next trapezium is 1.05 plus 1.12. And the last one is 1.12 plus 1.18. Okay. So what actually happens is that one you get one of those in the list. You get one of those in the list, 2 of each of the others. Okay, and that's the easiest way to remember it. It's a bit less messy in all this. So when you've got this table, you put all the x values in there. That gives you the right number of intervals. Work out the y's. The top one gets multiplied by 1, and the bottom one gets multiplied by 1. And the middle ones, they're all in 2 trapeziums, so they get doubled. Okay. So then you add all these up. That one's 0.83. That one's one's 1.92. Give myself a bit of room here. Next one, that's 2.10, 2.24, 1.18. Add them all up. So that adds up to 8.27. Just do a quick check there. 2, 4, 5, 6, 8, 8.1, 5, 9, 17, 17, 18, 19, 20, 21, 22, 2, 4, 6. Yeah. Okay, so it's actually a half times a half times 8.27. So half from the formula and a half from that. And a half from the formula times 8.27, which is 2.0675. So it's approximately equals to 2.1. So 1 dp. Okay. Example 2. The speed of an athlete t seconds after he starts a warm-up sprint can be modelled by the equation v is 1.7 e root t to the power root t minus a half t squared. It takes the athlete 6 seconds to run the length of the track. Use the trapezium rule with 5 intervals to find an estimate for the value of that one. 5 intervals from 0 to 6. Okay, so we've got 5 intervals running from 0 to 6. Each one's going to be 1.2. Next one 2.4. Next one 3.6. Next one 4.8, and the last one is 6.0. So that gives 1, 2, 3, 4, 5 intervals. Okay, so our x's are going to be 0, 1.2, 2.4, 3.6, 4.8, 6.0. Okay. They've got a picture in the book, and it looks like this. Okay, so when we're doing these trapeziums, it's always going to be an underestimate for this one because it's concave down. So it's going to be an underestimate, but you need the diagram to see that. You wouldn't be expected to do that in your straight out. So the V, which is 1.7 e root t minus 0.5 t squared. So these are t's, not x's. Okay, and again they've got these in the book. So that's 1.7, 4.36. So basically we're substituting these values of t into here. 4.36, 5.12, 4.86, 3.68 and 1.69. Okay, so again multiply the first and the last one by 1 and all the others by 2. 4.36 times 2. 8.72. 4.86 times 2. 9.72. 3.68 times 2. 7.36, and the last one is 1.69. So we've got to add those up. Remember here the step size here is 1.2. So it's 1.69 plus 7.36 plus 9.72 plus 8.72 plus 4.36. 98, I've done that wrong. 4.36 plus 8.72. I bet one of the decimal points didn't work. Plus 9.72 plus 7.36 plus 0.69 adds up to 31.9. 1.85. So it's a half times 1.2 times 31.85. Half from the formula, 1.2 from the step size, and 31.85 from that one. So divide by 2 times 1.2, 90. Oh, do you know what? I've missed off. Sorry. That one should be times 2, and that one's times 1 up there. I didn't do it very well there. 1.7. 4.36 times 2. 8.72. Let's get this right. 8.72 is that one. This one is 10.24. Okay, right, add them up again. 1.7 plus 8.72 plus 10.24 plus 9.72 plus 7.36 plus 1.69. 39. Getting it right now. 39.43. 39.43. Divided by 2 times 1.2. 23.7. Is that metres? Metres? Yeah, it will be. It's the length of the track, isn't it? To 1 decimal place. Okay. So I didn't really read into all the question very much. I just picked up the formula, which was there. Look, there's the formula there. That goes there. Let's find 6 seconds to run the length of the track. So it goes from 0 to 6. Then it says 5 intervals. So I've done 6 divided by 5 is 1.2. So these are going in steps of 0.2. That was by looking at the picture. So I didn't really know that picture off the top of my head. But once I'd seen it, I could see it was an underestimate. And so basically, because it's the length, these are metres per second. And these are seconds. Is it seconds? Yeah. So the length is the area, is the length, because metres per second times second is metres. Okay, so the area gives us the length. So we split them into trapeziums. And I missed this top one off because it was just by itself over there. So it's 1.7 times 1, etc., etc. I said all that bit, and that bit works. Right, that's that one done then. Where do I stop this going?